So in this lesson, we're going to look at what we call material takeoff forms for a material takeoff for concrete forms. Get the words in the right order. So basically what a material takeoff is, it's a list of materials required to do a job. So material takeoff is just another name for an organized list. It's how we would calculate the supplies that are required. I've kind of started you on the process you would need for doing some of this. It's part of the reasons why the first couple assessments that you did were getting you to think about how many materials would you need, what would you use to calculate it all. For concrete forms, we're going to look at first the different pieces you would need in order to cast the footing and the walls. And then we'll also talk for a couple minutes about ICF. Now, this is only a one lesson section. It's not long. I'm going to go through one example with you. I am posting a second example for you to review. And then there's going to be a hand-in assessment. So there'll be a little quiz for you to kind of check your understanding and see if you need any help with anything. And then there'll be the equivalent of a test, but it's not weighted very much just because this is such a short section. I just didn't want to include it with the last one because I thought it might be a little bit too much information all at once. So what we're looking at here is we're going to be looking at how do I calculate the number of forms I would need for the sides. We're going to find out how would you calculate how many feet of ribbon. We have ribbon and we have kicker that go around our concrete that helps hold our forms into place. How do we figure out how much of that we need? We'll look at okay, bracing. You need bracing in order to hold things in place because concrete is quite heavy. If you just put the concrete in without bracing, it would the force pushing down, we call that hydrostatic pressure. The force pushing down would push the forms out. So you have to have bracing to compensate for that. So we'll look at how we calculate those different pieces. Oops, I got subtitles on here accidentally. We'll see if we can turn them off. There we are. All right. So one of the things I am going to get you to think about is this is a very similar foundation. Looks a little bit different though, doesn't it? So here you can tell we have separate forms. They're all fastened together. Now these ones aren't plywood forms. It's one of the best examples I could find. I do have another image for you. But this should look familiar to you from a little setup that you have near the bulletin board in the shop. These are your ICF blocks that they've built a foundation with. So sometimes we calculate using sheets of plywood, which is what we're going to do for this section, simply because as technology changes, it's been changing quite quickly, moving towards lots more ICF being used. So styrofoam blocks that you pour your concrete in instead of putting sheets of plywood up. Your books haven't been updated quite as quickly. So we still go back to the old school way of doing it with plywood. But I do realize that nowadays we're often using ICF. And I'm going to give you a little video that this image comes from to kind of watch. I'm going to give you a page to look at. That'll be part of your assessment to kind of compare and contrast where you think things will go and some of maybe the advantages and disadvantages. I should say, yeah, there's disadvantages, I suppose, to ICF. But it gives there's a couple really great summaries. So your assessment for this section will be a little bit of math coupled with a little bit of thinking rather than just your traditional regurgitate. Because you're going to see, I'm going to give you all the formulas. So just copying the information doesn't necessarily make sense, but thinking about how you can apply it does. So you'll notice here, there's bracing up along the top. So that's important to hold the foundation together. There's vertical supports with braces, just like you had before. You'll notice there's these bars around the outside. Now these are wooden bars. We're going to look at some other types of bars that we use when we use ICF. But one of the big keys to think about is when I use plywood forms, the plywood all comes off the forms and leaves you with your bare concrete walls. But when you use something like ICF, you leave the styrofoam in place. So I'm going to let you think about what are the advantages. And you don't have to think about environmental efficiency. Think about it like a carpenter. Think about it like you're a laborer starting your first job. You're the rookie on the job. You're on a job where they're doing concrete work. Imagine you have to lug the plywood forms in to set up the foundation. Then they have to be removed and pulled back out. Then you have another job where you use these ICF blocks. Does the styrofoam come off or does it stay? The styrofoam stays. What would be some work advantages? And it's only a 2-minute video I'm going to give you to watch. What would be some of the advantages from a work standpoint? And I can think of quite a few if I had to do the job, that's for sure. All right, so you'll see that there's a few similarities that we have here. So we're going to go through each of the pieces that you're going to need for pouring a form. So we're going to start with, I'm just going to kind of talk through what the formulas would be and how we calculate them, and then I'm going to do an example with you, okay? So we're going to start with the footing because the footing gets done first. So this is a nice small little footing, obviously not a house, but a little footing, and it gives us a really good visual. So you have form sides. So on each side of your footing, you need wood. That wood is what holds the concrete in place. So that's our form sides. You'll notice the length of it is double the center line perimeter. So it's double the center line perimeter. That's really important. You need some inside and you need some outside. So for the total length of the amount of material you would need to do concrete, you're going to need double the perimeter, one for the inside perimeter, one for the outside perimeter. We're going to talk about a word, effective form length. We'll wait and we're going to talk about that just a couple slides in. We'll come back to that one. I need to know how many pieces of lumber I need. So I take my center line perimeter, and as we said, we need double the perimeter because we've got to put some wood inside and some wood outside. And then we're going to divide that length by the length of each piece of lumber. Okay, so form sides are pretty easy. You find out how long is the section, what's the perimeter. Okay, you got to do inside and outside, so we double it, and then we're going to divide it by the length of our lumber. And we're going to use a special length. We're going to use what we call the effective length. We'll learn what that is in a minute. What else do we need for a form footing? Or a form footing or footing form? You need stakes, okay? So based on your book, they use 400 millimeters for the standard stake length. So we're going to stick with 400 millimeters. I assume there's a reason why that's what's recommended. So you need stakes on each side. So the total length that needs stakes is going to be double the center line perimeter. You're going to be told how far apart to space them. It's usually 1200 millimeters or 1.2 meters, but we'll look at that when we get there. So you're going to find out, okay, how many stakes do I need? I take my perimeter, I divide it by how far apart the stakes are, and then I have to double it for stakes on each side. But we're figuring out a material list, so just the number of stakes doesn't help. Well, I mean, I need that, but how much wood do I need to make those stakes? So to find that, we're going to find the number of stakes we can cut out of each board. And that's pretty basic, just the length of your lumber divided by 400 happens to be the length of the stake. If the length changes, you would change that number. And then you figure out how many pieces of lumber. So you know how many stakes you need, you know how many pieces you can get out of a board. So we're going to calculate how much lumber we would need. Cleats are another piece that we'll talk about. Cleats are the pieces that are across the top here. You see those little pieces? Cleats, they keep the form standing straight. Without the cleats, it would fall over. The cleats keep it upright. So you've got stakes to support it, plus those cleats to keep it in. And so what you do, because they have to be a little bit longer, now these look like a metal cleat, appears to be a metal cleat. We're using a wooden cleat. They say add 100 millimeters, so slightly wider than the width of the footing, so that you have something to fasten to. And we'll look at how we calculate that when we get there. Now cleats, you'll find you only need one center line perimeter because, well, one cleat crosses both boards. So the cleats are just spaced around one perimeter. And then we're going to need a keyway. Now there's not a picture of a keyway here, but a keyway is just a piece of lumber that makes a groove down the middle of the footing so that when you pour your walls, it helps it situate inside that groove and add strength. Okay, so that happens to be our keyway. I'm hoping you've talked about some of these pieces with Scott, so you're a little bit familiar, but if you're not, shoot me a message, let me know. I'll give you some more pictures, give you some more examples. All right, now let's take a peek at our next slide here. Okay, so now we need forms. So that's our footing pieces. and we'll do footing calculations. We're going to calculate the two of them separate, but because we're doing it for the same foundation, I'm going to do them one right after the other. So we'll do both explanations right at the start. So what about when we do the walls? Now this is a better example of the walls than perhaps what you had before. So when you do the walls, we need form plywood. So you'll see here there's plywood along the walls. Here we see form plywood. So you got plywood on this side and plywood on that side. That's why we double our centerline perimeter. It's because we need plywood on each side. It says install plywood vertically. It depends on how tall the walls are. If your wall is just a short wall, you might find it's more effective to rotate it sideways because you need less pieces. So you'll want to watch if the plywood's installed vertical or horizontal. The questions, I know in the quiz, the questions will change a little bit. What happens if it's vertical? What happens if it's horizontal? And it's just going to change the number of pieces. So if it's installed vertically, the narrowest width of a sheet of 4x8 plywood is 1.2 meters. So you're going to take your perimeter, you'll double it, and then you divide by the width of your sheet of plywood, which is 1.2. If instead, I'll use my phone as an example, if instead of installing a plywood this way, if we rotate it to this direction, this length on a sheet of plywood would be 2.4 meters. So instead of dividing by the width, we divide by the length of the plywood, so we use less boards. That's if we have a short wall that's less than 1.2 meters tall. Okay, so your questions will specify, it's not really that big of a deal other than you'd pay more form rental if you did things the other way. And if you have to move it, it's a lot more moving. You'd be moving twice as many sheets if it was just for a short wall. All right, so we talked about plywood. Plywood's on both sides. Snap ties, what are they? Snap ties are these little bits right in the middle. If you have a basement with a poured foundation, go down, especially if you have exposed concrete walls, go down and take a look and see if you can tell where the snap ties were. If you go down in my basement, and I don't know if I could get a good picture. I didn't try to get a good picture. I always say I'm going to, and I never end up doing it. But if you look on the wall, I can see on the wall, there's these little tiny, like little circles, and you can tell that's where the snap ties were that hold the weller bars are. They're perfectly lined up, and I could count off per sheet how many snap ties there were. So snap ties, they hold the two forms together. And then on the outside of the snap ties, you'll see these little bars, they're called whaler bars. You can see them along here. So there's whaler bars, and they go in and it holds the plywood perfectly separated for the exact amount that you need for your footing, your form width. Okay, so those are your snap ties. To find out how many ties you need, we need one snap tie, goes through two pieces of plywood. So it's kind of like doing cleats. You take your perimeter, and we'll know how many snap ties we need for a sheet. So we're going to divide it by how wide our plywood is to figure out, okay, how many sheets of plywood are there if there's only one side? And then you multiply by how many ties there are per sheet. There's actually two ways we could find the snap ties, and we'll look at both when we do the example. Whaler bars are the strips around the outside, and we're going to come back and we'll talk about effective bar length. We'll leave that for now, but effective bar length, we're going to find these bars overlap, which shortens up their length. So we'll figure out how to find the effective length, or the actual length we'll use to calculate. There's going to be the same number of rows of bars as there are of snap ties. So if there's 5 rows of snap ties, you'll have 5 rows of bars, which would mean you need 5 times the perimeter on the outside, and they also go on the inside, so you'd have 5 times the perimeter on the inside. So we kind of double the number of rows since the bars go on each side. So to calculate it, I say lumber pieces, it should say whaler bars. Number of whaler bars is going to be a perimeter doubled, because you're inside and outside, times how many rows you have. And then at the end, we're going to divide by how long are our bars. And the last two pieces that you need for outside are braces. You see braces here. You know, they have to go around the whole foundation, and you find out, divide by how far apart they're spaced. And the braces are typically always set up on the inside. And you'll have a ribbon and a kicker. You'll see up at the top here, that's our ribbon. And a kicker is going to go at the bottom. Kick with your feet, kicker goes at the bottom, and it keeps the form from kicking out. Okay, so those are all of the pieces that we would need. There's a lot of pieces there. Take a second when you have time, especially when you get to doing your assessment, I'm going to want you to stop and think about all the pieces that you need to calculate, and imagine, what if we had ICF instead? Would you need snap ties? Take a look at the ones in the shop and see, would you actually have to put something inside to keep them spaced apart, or is there something there? And a few of those things, think about how much plywood you'd have to haul around and how heavy it is, and check out one of those blocks and think about, would there be some advantages, even just beyond insulation factor, for using ICF instead of this older method that has been traditionally used. Now we're going to find, as we calculate, we're going to calculate if we had to make all the forms. I do realize, I'm going to say right now, I realize that you rent them in most cases, but even if you're renting them, you'll want to know how much you would need, or you could end up working in an office where they rent them and you would be the person calculating how much is needed. So you never know where life is going to take you or what job opportunities might open up. If you don't like winter work outside, a calculation job inside is an alternative, and you still have to know the theory. All right, let's turn off this pointer so I can go back to my pen. So what does end lap mean? So we're going to see questions that say end lap and effective length. So I kind of skimmed over that before I said I'll get to it on its own slide. So end lap is just, let's see if I can get some, every now and then my tablet doesn't want to communicate. Let's see if we can get it to communicate here. Should be working now. No, not sure what's up. Sorry about that, folks. All right, so what's end lap? We'll talk through it while I try to reset things here. So end lap is the amount of overlap between two boards, okay? So because the two boards are overlapped, they're not quite as long as you would expect them to be. And because they're not as long, oh, I know why this isn't working. I put the wrong cord plugged in. Brilliant move. Explains why my phone kept turning on and asking for me to. There we go. We're good now. So this is our overlap or end lap, and it reduces the amount of material that's in contact, because you'll see here the board, let's say the board is actually this long, but not that whole length is in contact. Okay, and this board, not all of it is in contact. So what we do is we subtract the overlap. And if it's overlapped equally everywhere, we can assume that the overlap on each piece is the same. So the actual length would just be, that would be our effective length, just the piece that's not overlapped, because we would assume over here, there's going to be another overlap board. So these are obviously cut off, which is kind of trying to show. So it reduces the effective length. The effective length of the material is the actual useful length after the overlaps are taken off. So to find effective length, you're going to take your material length and we just subtract the overlap. So nice and easy to do. We're going to have to do that several times. Anytime you see the word end lap, we're going to subtract the overlap. First thing we have to do in order to figure out our material list is everything is based on center line perimeter. So we have to calculate center line perimeter and we need to make sure it's correct. I've seen a few order of operations issues come up, so we're going to calculate it. Let's change it to meters first, because it's going to be way easier to work in meters. We're going to flip back and forth between meters and millimeters a little bit in these questions, but for a center line perimeter, it's much easier to have meters to start. So the formula, there's no jog in this, so it's 2 length plus width minus 4 foundation thicknesses. So 2, our length, 13.6 plus 9.8 minus 4 times the thickness of 0.2. Make sure you follow order of operations. Add this, do this section first, add, then multiply. You may have a calculator that will do the order of operations for you, but if in doubt, if you're not getting your answers correct, put your center line perimeter in your calculator and do it step by step. So this gives us 46.8. 0.2 times 4 gives us 0.8. You subtract the 2 and we get 46 meters. So that number is going to be important to go to. We're going to go to this number on a regular basis, and a couple times we're going to pop back to this screen. All right, now we can actually dive into calculating the materials. Now you're going to have a form. It's got the equations. I'm going to give you the equations here, but when you get to your assessments or your quiz on SAM, you won't have them. You'll have to come back and look them up. And this is something, unless you're doing it all the time, I'd expect you to need to look up. So I'm going to get rid of the video because it's not very bright in here. You can't see me very well anyway. And we're going to work through our calculations. I apologize. The lines are a little small. So hopefully you have enough space to write. So this is our lumber description that we have here, and it gives us some extra information that we need to have. The total column is just how much material I'm going to need. So you'll see here, I'm starting with the strip footing. So we're going to start, this is everything we need to calculate the materials for the footing. So first of all, I need sides for the footing. And we've got all of our steps here that help us. So it goes around double our center line perimeter, but we've got end lap of 400 millimeters. So we need to find the effective form length. So I'm going to start with that. So we said the effective length is just the length of the material minus the overlap. So the length of the material is 3,660 millimeters minus 400. You'll notice it gives us the specs in both metric and imperial. It's easier to work in metric with this rather than flipping between feet and inches all the time. So 3660 divided by, minus 400 gives me 3,260 millimeters. Here's our effective length. Now we can calculate the number of pieces of lumber. So the number of pieces takes our center line perimeter, which was 46, and maybe we'll just write that up here, just so we have it for reference. So the number of pieces is 46 meters. Times 2, because it goes on both sides, that makes sense, divided by the effective length. If the effective length is 3,260 millimeters, I need to put that in meters. So you'll notice we did a lot of meters and millimeters conversion. 3.26 is the length we would use. So watch for meters. Okay, if you take 46 and you divide 46 and you multiply it by 2 and then divide it by 3,260, it's going to give you like a decimal. It doesn't make sense that you would need less than one piece for a 46 meter foundation. So that's an easy check using some logic. How many pieces do we need altogether? If you plug that into your calculator, you will find you need 28.2 pieces. Now I'm keeping a decimal here just because it says allow 5% extra. I want to calculate my 5% before I do any big rounding. So I'm keeping just a little extra accuracy, 28.2. 5% is 100% of what I need plus 5% more. So it's like multiplying by 105% or 1.05. That goes back to last semester. So multiplying by 1.05. Now this is going to be our final number, so we will round it. We get 29.6, which rounds to 30 pieces. So we need 30 pieces of lumber altogether. So you can see how this just kind of keeps organized for us. I actually think this would be a great section to make an Excel project for you. I'm going to skip that this year. Maybe next year I will throw the Excel project in, but because it would be great. You could plug in your center line perimeter and we could actually have it all set up to calculate everything that you would need. Be a really great tool. Next thing, how many stakes do we need? So a few notes, reminders. We need stakes on each side. The number of stakes is my perimeter divided by how far apart the stakes are, doubled because they go on each side. Okay, so I can find the number of stakes. The number of stakes I can cut out of a board is the length of the lumber divided by 400. That 400 is because it comes from here. And the plus minus just means approximately 400. So if it was 398, it wouldn't be a big deal. And then we have to find out how many pieces of lumber will it take to get the number of stakes. So let's just start with the number of stakes. And every once in a while, I'll spell steak like the steak you eat instead of the steak you drive. I catch myself sometimes after the fact. If I've done that, I apologize. I know I haven't here. Every once in a while, you might see that pop up unintentionally. So the number of stakes that we need is equal to our perimeter, which is 46, divided by the spacing of the stakes. So 46 meters. Our spacing is in millimeters, so we're going to have to divide by 1.2 meters. And we need stakes on both sides, so we're going to double the amount. So 46 divided by the spaces doubled gives us 76.7 stakes. Okay, it says to allow extra, and we want extra stakes. So we'll add the extra in now. It's usually better to add the extra on this number of small pieces rather than after you found your total lumber amount, because you might not need a whole piece of lumber to get 3 extra stakes. It might be okay if you just add the extra now. It might end up being the same amount. So usually it reduces waste. So we're going to add the waste in here. So we'll add in the waste. So that's our 5%. So we'll take our 76.7. We're going to multiply it by 1.05 to add 5%. And that gives us a total of 80.4, which rounds to 81 whole stakes. So this is the actual number I need with waste. Okay, so I've got the first part figured out. Now I need to know how many stakes can I cut out of a board. So the number of stakes per board. To find that, we find how long is our board. So 3660 divided by how long is each stake? Well, they're 400. And you'll see I didn't switch to meters. I've left everything in millimeters because the length is in millimeters, and I guess both lengths are in millimeters. So we know both of them in millimeters, so we don't have to switch back and forth. Okay, so use that. Don't convert unless you need to. But I like reducing the zeros on my centerline perimeter because it's easy to miss typing a 0 in your calculator. So if we take this, 3660 divided by 400 will give us 9.15. And we're going to round down because there's only 9 whole stakes that are useful. So I can cut 9 stakes per board. Now we find out how many boards. So the number of pieces. Well, I need 81 stakes. I can get 9 out of each board. So 81 divided by 9 leaves me with 9 boards. So I need 9 pieces of lumber that size. Not complicated, just a lot of little steps. You'll see why I didn't include this with the last section. Next, we have to calculate cleats. So for cleats, it says add 100 millimeters to the width of the footing. So we're going to have to flip back to the width of the footing. The footing is 600 millimeters wide. So I'm going to need my cleats. We have a 600 millimeter footing. You could add the 100 on now. Yes, we will add the 100 on now because I maybe adjusted the formula a little bit in here. Okay. So we need to find out the number of cleats first. So let's first find out the number of cleats. So the number of cleats, you only need 1 for both sides. 1 looks after both sides, so we just need 1 perimeter. So we'll take our perimeter, which is 46, and we're going to divide it by the spacing, which is 1.2. It's a magic number based on plywood width. So 46 divided by 1.2 leaves me with 38.3. And then we add our waste, 38.3 times 1.05. I always add the waste on right away because I've got the number in my calculator already. I can just hit multiply and put the 1.05 in right away. And that leaves us 40.25, which rounds to 41 cleats. Okay, how much lumber do I need to cut 41 cleats? Well, I need to find out how many cleats per board. So we got the first part done. How many cleats per board? Well, each cleat is 600 plus 100, which is 700 millimeters, okay? So I need my lumber length divided by the cleat length. So the number of cleats per board is going to be equal to 3660 divided by 700 millimeters, which will give me 5 decimal something, but the little part is not, that looks like a 6. The little part that's left over is not useful, so we round it down. Doesn't matter how close it is, we always are going to round down. So this is 5 cleats per board. How many pieces of lumber? To cut 41 cleats, if I can get 5 per board, well, 41 divided by 5 will give us 8.1, which would round to 9. We need the extra 1 because it would be too much space. We need 41. If I round down to 8, I'm only going to have 40. So we'll round up to include the extra. I mean, we could probably argue it because the 5% extra left us with 2 extra cleats. Actually, only left us with 1 extra cleat. So you could say, well, you might be okay, but what if one breaks or falls apart or something? You want to have an extra on hand right away. So we'll round up to 9 pieces of lumber. That would allow us to cut a few extra pieces. Okay. And the last piece we need is the keyway. So for a keyway looks like this. It's just a little groove, or in this case, it says rip in half at 15 degrees. So keyway may look more like that, just like a little divot in your footing, so that when your wall goes in, the concrete's going to go in here and it's going to help stabilize that wall on top of the footing. So how do we cut it? Well, a keyway, you take a piece of lumber and we rip it in half at 15 degrees, and that gives us something we can make the keyway with. Sometimes people will just drag a piece of lumber through it. Other times people will actually set a piece of lumber in so that they get a good imprint. How it's done will vary, but we'll teach you how to calculate it really quickly. So it says, if we're going to rip them in half at 15 degrees from one piece of 2x4, you can get 2 keyways. So to get the number of pieces of lumber, you take your perimeter, you divide it by 2, because one 2x4 is going to give us enough would give us enough for two perimeters. So we just say, okay, if we had half the perimeter, the lumber for half the perimeter would do the whole perimeter. So we're going to do 46, and we divide it by 2, and then we divide by the length of our lumber, which is 3.66. Get the millimeters out right. And it says you don't have to add any extra, and that's because it's not a spot where you're going to have waste. You don't have to worry about that. And we would need 7 pieces. Okay, so for the total column, always rounds up. Okay, always rounds up. But if you want to find out how many boards you're cutting out of a piece of lumber, you're always going to round down. So that's our footing. Not horrible calculations. They're not difficult, especially if you kind of have the steps beside you. They're all pretty logical. I would argue, other than maybe not knowing how much material goes on each side, if I gave you a question, how many stakes could you cut out of a board? That should be a first semester question. Those questions shouldn't really stump you, but sometimes we just need to be reminded when they're put together with a lot of other information. All right, so the next one, forms are easy. They're the easiest part of it all. I will change, I left measurements in here. We'll leave these measurements out for now. Because we're going to refer back to our blueprint, and I don't think I have the same measurement on the blueprint. I popped this image in. So pad footings. So we have to have some footings in order to have some supports. They require extra support underneath them, so we have to pour those footings. So it says the form should be at least 100 millimeters longer. So first of all, I'm going to tell you what this side forms run wild. So when they're doing forms, they don't necessarily use a piece of lumber that's an exact measurement. See how this one's longer than this one? That's perfectly okay. So what they do is they just let them run off to the side, and it doesn't matter if it's longer as long as they get the right size inside. Now, it says the form needs to be 100 millimeters longer than the pad dimension so that you have room to fasten it at the corner. Okay, so that's the biggest reason for adding that 100 millimeters. So we're going to find the bare minimum, but oftentimes they'll use longer pieces just to avoid having to cut new materials. And you never need any extra because there will always only be 4 sides. And as long as your side, you've calculated the side actual length, then there's nowheres you would ever have waste. So let's take a quick gander back and we're going to check at how big our pads were. Oh, I guess I could have left the measurements there. They're 900 by 900 by 150. So let's go back here. Oh, this one I do have to change it because they're a little different thickness. 900 by 900, let's throw in our new thickness here. Instead of 200, we'll throw in 150. Okay, so what they do is they bank the ground. See how the pad doesn't go all the way down the bottom? They make the form up and they use the earth to kind of bank it up so that you don't have to have the full depth. So that's often used. Okay, let's figure out our sides. So first of all, we need to figure out how many sides can I cut out of a piece of board? Well, we've got a 10-footer, which is 3,050 millimeters. And my pads need to be 100 millimeters longer than the dimension. The sides need to be 100 millimeters longer than the dimension of the pad. So 900 plus 100 gives me 1,000 millimeters or 1 meter. Now you'll see here, my lumber is 3,050 millimeters long. I will write out the math, but you hardly need to. 3,050 millimeters divided into 1,000 millimeter sections gives me just one sec here. I'm going to just do a quick pause. I think we're back. I just had a program show up and want to install something on my computer. We don't want that happening in the middle of this. Okay, so 3,050 divided by 1,000 gives me 3 pieces per board. So how many pieces do I need altogether? Well, I can cut 3 sides out of a board. The plan, if we looked at our plan, if you need to take a flip back, or hopefully maybe you printed off the notes for this, there were 3 pads. So we have 3 pads times 4 sides means I need 12 sides. I can cut 3 per board, so we divide by 3, which gives us 4 pieces of lumber. Easy calculation. Number of pads times number of sides divided by the number of sides you can cut per board. Then you need stakes for each corner. So the number of stakes is the number of pads times 4. So the number of stakes is going to be equal to 3 pads times 4 stakes each, 1 for each corner, gives me 12 altogether. How many stakes per board? Oops. Okay, the stakes per board, well, it's the same dimensions really as we had before. 3660 is the length of the board divided by 400. I can use both of them in millimeters since they were already given in millimeters, which leaves me with 9. So how many pieces of lumber? Well, I need 12 stakes. I can cut 9 out of a board, so 12 divided by 9 leaves me with 2 pieces of lumber. And you might even be able to argue you'd have enough in the 5% extra from the stakes to do the footing. But I mean, that's an argument up to you to make if you really wanted to. So not too bad to calculate, just lots of little pieces. But if you stop and think about it, they're pretty logical. We have one section left to calculate. So we've got the forms, sorry, getting my words mixed up. We've got the footing calculated. That's all good. We've got the pads calculated. That's good. Now we just need to know what we need for the walls. So for the walls, we've kind of talked through the pieces. We're going to start with our plywood, then we're going to find snap ties, and we're going to find the bars that hold it all together, and then we'll deal with the braces and the kicker. How much plywood do we need? Well, it says install it vertically. Part of that could be proven from the blueprint. If you were to look back at the blueprint, the walls are 2,400 millimeters high. The plywood, that's 8 feet, is 2,400 millimeters high if we install it vertically. Okay, so vertical just means I'm installing it in that direction. Sometimes it'll say horizontal. If it's horizontal, we're just going to rotate it. And in that case, you'd only have a wall that's 1.2 meters high. Watch for that on the quiz. Keep an eye out for that. You consider yourself warned. All right, so we need double the center line perimeter, and we divide it by how wide our plywood is, and then we'll add our 5% extra. So easy calculation. 46 is our meters is our perimeter. We're going to double it because plywood goes on both sides of the foundation. Then we're going to divide by how wide is each sheet of plywood, and it is 1.2. So I'm going to label these height and width, just in case you're looking at that red box thinking something else. So then we divide by the width of the plywood, which is 1.2. This will give us a total plywood quantity of 76.7 sheets. Okay, now we add our 5%. 76.7 times 1.05 leaves us with 80.5 or 81 sheets. And you can see why you'd rent them and reuse them is because that's a lot of material. And if you're talking OSB, that's right now it's somewhere close to $30 a sheet. Quick math on that. That's like $2,400 just in materials for plywood. That would end up being wasted. So usually we rent them to save those costs. Snap ties, they're going to go between our plywood. Now this formula, it comes from the ILM for this section, but there is another way to calculate. I'm going to give you both of them, and it will be up to you to choose which way makes the most sense for you. Now, SAM, when you're calculating, is based on this formula. So if you have a question in SAM, please use this formula. Okay? But I will give you an alternative. The reason for using that formula is SAM may have issues getting the rounding perfect on that question. I will try to increase the tolerance a little bit so that it allows for variation. We'll see. There's going to be a little bit of a difference between what we calculate the two ways. So what it says for the number of ties, one tie goes between two sheets. So we take our center line perimeter, we divide it by how wide the plywood is because we want to figure out what's the amount of plywood needed for one side, and then we're going to multiply it by how many ties per sheet. So the number of ties is our center line perimeter of 46. We're going to divide it by how wide the plywood was, which was 1.2. And then we're going to multiply by how many ties each sheet has. And each sheet has 20. It has 5 rows of 4. Sometimes that number might be 15. That's another common number that comes up. So do watch for that. So 46 divided by 1.2 times 20 leaves us with 766.7 ties. Plus extra, 766.7 times 1.05 leaves us with 805 ties. Okay. What's the other way to do it? Well, the other way, and it was a student that brought this up to me. Sometimes teachers take the longest route. Sometimes students have really good ideas, so I welcome you sharing them. One student said, but I already know how many sheets of plywood I need. If I just took that number and I divided it by 2, because one tie goes through 2 sheets, and multiplied by how many ties per sheet, will that work? And it will. So the alternative is number of sheets for the walls divided by 2 times number of ties per sheet. Okay, so in this case, I'll do the math out over here. 81 divided by 2 times 20. If you do that, and that 81 already has 5% extra. So if the extra was already included in 81, the extra sheets, it's also going to mean there's extra ties. And if you do that calculation, you would have 810. So that's kind of like a two for one question. So I would accept both 805 or 810 because both of them are very accurate ways of calculating it. I would argue this version saves you adding in the 5% because it's already there. So that was a really good thinking example that I've had from last year or the year before. I can't remember when it first showed up. Now, how many Whaler bars we need? You'll see effective length. Whaler bars overlap. Okay, so you have your bar, and to increase strength, we overlap them a little bit. So we have to, and you'll see here, there's our lap. So we need to figure out what is the effective length. Now they're 3 meters long, they're overlap 300 millimeters. So that means 3 minus 0.300, keep everything in meters, equals 2.7 meters for the effective length. Make sure you subtract millimeters from meters. 3 minus 300 is not going to work very well. That would give you a negative, so that'll be a clue for you. So, and the number always is this pretty well always the same for that. Occasionally it might change just to see if you're reading the question carefully, but to find the effective length, it's just the length minus the overlap. Just make sure you're subtracting meters from meters. Number of rows matches the snap ties, so there's 5 rows. We have to double the number of rows since bars go on each side, and the formula is given for us here, and this instead of lumber should be bars. They're not really lumber, they're metal bars. All right, so the number of bars is equal to 46 our perimeter. Bars go on each side, so we double it. There are 5 rows on each side. So we multiply by the number of rows and then we divide by the length of the bars. So 2.7. And that will give us 170.4 plus waste equals 170.4 times 1.05 leaves me with a grand total of 179 pieces. It's not too difficult. The easiest two are, I think, the last two. Braces and stakes. So braces, it says allow 1 piece every 2.4 meters around the perimeter. And you only do it around one side of the perimeter. Now, for some reason, that doesn't necessarily make sense to me that you only brace the inside. I feel like there should be some bracing on the outside. But I have asked, I have confirmed, you only allow around one perimeter. They brace the inside, not the outside. So we will leave it be at that. That's what I've been told, so that's what I'll stick with. Subject experts have spoken. So the number of pieces is going to be equal to our perimeter, which is 46, divided by the space of 2.4, which gives us 19.1 times 1.05 leaves us with 20 pieces. And the very last one is the ribbon and kicker. So it's double the center line perimeter. It goes around the bottom on one side and it goes around the top on one side. So that's an easy calculation. We're going to do 46. We double it because it goes around the top and the bottom, and then we divide by our length of lumber, which is 3.66. And we don't actually have to add extra for the ribbon and kicker. It's kind of like the keyway. So 25.1 pieces. And that's, oops, 25.1. Let me see. I should have rounded that to 26. I have it written on my sheet to be a 26. Helps when I write the same thing down. So let's just switch that up. So that's all the calculations that we need for calculating the amount of material you would need for your forms. So I'm not going to do another lesson on it. I'm going to post you another example that you can work through. But because you have all of the formulas and it's not something that I could really test you on, unless it's open book, and with open book, even with all the formulas, it's kind of, you're just copying your formulas. I'm going to give you an assessment, and the assessment will get you to think a little bit about some differences between ICF, and I'll give you a few links that I have found really helpful that you can use to read and analyze and think about how would that impact from a work perspective, but also how would it impact making a material takeoff. What would it mean for the number of calculations you might need to do? And I know you may not have experience with it yet. That's okay. Part of it is I want you to think and apply. And if you're able to think and apply in a way that connects the learning with real life examples to the best of your ability, I really can't ask for more. That's part of the purpose of this section. Now, just as a heads up, this section will not be on your block exam. You do not have to have these pieces all memorized. One type of question a block exam could ask is, how much material would be needed to do foundation footing? That's a good block exam question, but you will not have to complete a material takeoff form. So that should take a little anxiety away from that and should have you good.